Okay, everyone. So make sure you have a coffee or a cup of tea. Let's have a look at this question here. So 7.2. 3 planks are collected as shown by bolts 15 millimeters diameter, spaced every 150 millimeters along the longitudinal axis of the beam for a vertical shear of 10 kilonewtons. Determine the average shearing stress in the bolts. So first thing we're going to do is obviously use our shear flow equation. So we know the V. It's 10,000 newtons. Let's work out the I next then. Which I can't do because I don't know the neutral axis. So let's work out the neutral axis. So that's the sum of our AYs, our Qs, divided by our areas, sum of. So I've got 2 located here and here. It's 1, it's 2. Which has a width of 125 times 100. Its centroid is going to be what? This distance is 150, so that would be 200 to get to there. So 2 of them, and next one is going to be 100 and 250 height. Its centroid is 125 divided by the areas. So that gives me neutral axis of (162.5). Just looking at Arnold's solution here. I can't seem to find whether I'm correct or not. Yeah, yes I am. Okay, so next let's find the I. So we're going to have to use the parallel axis theorem. And sum the sections, rectangle sections. Right, so 165 will be about here. So the parallel axis theorem for the top two sections, got two of them. 2 times by their area, 125 times 100. What's the h going to be? That will be 200. Take away 162.5. That turns out to be 37.5 squared. Right, now we've got two of these, so 2 divided by 12 will make that 16. And their width is 125. Their depth is 100 to the power of 3. So that's done the two sort of squarish sections. Now for the middle column, so its area is 100 times 250. Its h is going to be what? Well, I'll take the 250, divide it by 2. So that gives me 125, so that's the middle. And now I want to take that away from the neutral axis, which is at 162.5 there. I'm only interested in the distance. Actually, I should know this for T-beams. It works out to be the same. 37.5 squared. Okay, so that's that's our parallel axis theorem applied. Now let's do the 112b d to the power of 3. Right, that's a lot of stuff to stick in my calculator. 2 times 125 times 100 times 37.5 squared plus 16 times 125 times 100 to the power of 3 plus 100 times 250 times 37.5 squared plus 1/12 times by 100 times by 250 to the power of 3 gives me a big number, and probably not the right one. So Arnold is getting something completely different. So I'm getting 100 and I'll try again. 104.7 times 10 to the 6. Let's see if I've done that correct. 2 times 125 times 100 times 37.5 squared plus 16 times 125 times by 100 to the power of 3 plus 100 times 250, yep, times 37.5 squared plus 1/12 times 100 times, times 100 times 250 to the power 3. And I get a completely different number. So yeah, I didn't put it in correct. This time I'm getting that. 2 to 1.35. That's what Arnold got. So let's go with that. So we've got millimeters to the power 4. Here, this is millimeters. Right, so that took a bit of work. I've now got the V, I've got the I. Now let's look for the Q. So here you've got decisions. What do you want your Q to be? The logical thing would be to imagine we're going to take one of these blocks and we're going to try and shear it away from the rest of the body. So I'll take this block here, and I imagine that this is now going to try and get sheared away from that other block. So let's work out the Q for that. So the Q is the area times its centroid. Right. So where is it shearing? It's shearing at 200. So well, let's put it in this area first. So that's 125 times its height. So its width times its height. What's the Y going to be? Well, in relationship to the base, the bolt is located at 200. And the neutral axis is this one here, 162.5. So that's our Q. Notice I'm working in millimeters. So 468.75 times 10 to the 3. This is millimeters, so it's millimeters to the power 3. Okay, so we've got the B, the Q, the I. So we know the shear flow now. Then you've got to think about, for the two sections that we're trying to pull apart, how many bolts are there involved? It's actually strictly speaking just one. Okay. Now it's tempting to think that I need to double the bolt number or something like that, because we've got this shearing and also this shearing, which we could do. So I mean, we could have assumed that the middle section was shearing away from those two blocks, but if we did that, then we would have to say that there's two bolts being sheared. By looking at this, just this section on the left, I'm now assuming that I'm just shearing through one bolt. So that makes that particular statement a little bit easier. So if I was doing Q, what would be QS allowable force, it would simply be that the number of bolts here is going to be 1. Alright. Right, so what we are asking to determine the average shearing stress in the bolts. So the bolts are 14 millimeters diameter. They're spaced 150 millimeters long. So look at this equation here. So this is the equation here for force. We are looking for the stress in the bolt. So the N, that's straightforward. That's a 1. The Q we can find. So that is 10,000. Our work in millimeters. S is 150. Sorry, I haven't finished my little Q calculation yet. So V is 10,000. Big Q is 468.75 times 10 to the 3. My S is 150. And my I is 221.35 times 10 to the 6. Okay. So that's the force that's been exerted, and I want to know the stress. So I'm going to divide it now by the area of the bolt. So that will be pi. Diameter is 14 millimeters. I'm working in millimeters. Divide by 4. So what's that? And that will be the stress that's being experienced in one particular bolt. So 10,000 times 468.75 to the power of 10 to the 3 times 150 divided by 221.35 times 10 to the 6 times by pi times by 14 squared divided by 4. I use pi d squared divided by 4 for area. And that gives me 20. Remember, we've worked in millimeters. So that's newtons per millimeter squared, which works out to be megapascals. Okay, yeah, and that's same as Arnold. So there we go. That's 7.2 done.